Here are the Lesson 1 activities for college algebra. So this is just a lot of review skills. I'm going to work through it quickly. Be sure to reach out to your instructor if any of these are too fast and you need further explanation. Okay, so 2x plus 5 times 4x minus 7. This is a multiplication problem. People learn different names for the technique here. It can be just you distribute everything to everything else. Some people use the acronym FOIL, first, outer, inner, last. Some people use the lobster claw method, which just means draw a lobster claw. Oops. So that's your lobster claw. And it represents first, outer, inner, last. So the first terms, 2x and 4x, we multiply those together and you get 8x squared. Then you look at your outer terms, your 2x and your minus 7. You multiply those together and you get minus 14x. And then your inner terms, 5 and 4x, multiply those together and you get plus 20x. And then your 5 times your negative 7 and you get minus 35. And then combine your two like terms in the middle. We have 8x squared plus 6x minus 35. Number 2 looks very similar, but the difference here is that this is a multiplication problem because there's no operation symbol between the two parentheses, which we always assume to be multiplication. But this is a subtraction problem, right? So multiplication and subtraction are very different operations. So to subtract, we're going to take this negative sign and distribute it to each term in the second parentheses. So we have 2x plus 5 minus 4x plus 7. And then we just combine like terms. 2x minus 4x is negative 2x. 5 plus 7 is 12. For number 3, the square root of 1 over 49. When you're square rooting a fraction or you're square rooting a product, you can square root each factor separately. So this would be the square root of 1 over the square root of 49, which is 1/7. Okay, number 4, 3 root 12 minus 5 root 27. So it's helpful for me to have a list of perfect square numbers whenever I'm dealing with these radical type problems. So 1 squared is 1. 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared. Okay. So we look at the 12 and we say, okay, first thing to check is it in the list? Is 12 one of the perfect square numbers? It's not. Okay, so the next best thing we can do is say, do any of the numbers in the list divide into 12 evenly? Are any of these numbers factors of 12? And so you work your way through the list and you say, well, 1 obviously, right? But 4 divides into 12. 12 can be written as 4 times 3. So I'm going to go ahead and do that. This is 3 times the square root of 4 times 3 minus 5 times. And then I'm going to do the same game with the 27. 27 is not in the list, but are there any numbers in the list that are factors of 27? 1, obviously, but it's not helpful. 4, no. 9, yes. 9 goes into 27. If you don't know these off the top of your head, you just grab a calculator and you do 27 divided by 4. Not a whole number. Okay, 27 divided by 9, you get 3. Oh, okay, 9 is a factor. So we do 9 times 3. And then, just like with the previous question, I said when it's division or multiplication, you can do the square roots separately. So I'm going to break this up. So it's 3 times the square root of 4 times the square root of 3 minus 5 times the square root of 9 times the square root of 3. And then I can take the two square roots, the 4 and the 9. So this is going to be 3 times 2 times root 3. Minus 5 times 3 times root 3. I can do the multiplications, 6 root 3 minus 15 root 3. And now these are like terms. If this said 6x minus 15x, you would say, oh, that's negative 9x. But instead of an x, it's a root 3, and the rule works the same. You get negative 9 root 3. For number 5, we just play this same game. Okay, so instead of 72, I'm going to look through the list and find the largest number I can that is a factor of 72, and that would be 36. 36 times 2 is 72. So I'm going to rewrite my 72 as 36 times 2. And now there's letters in this problem, which makes it just a slightly more complicated version of the previous one. Instead of s cubed, I'm going to write that as s squared times s, right? Because when you multiply like bases, you add the exponents, so this would be s squared times s to the first, which is s cubed. And why did I do that? Because eventually I want to square root stuff in here, and square rooting a square is easy. Okay, same game in the denominator. Rewrite 8 as 4 times 2. And then there's nothing I can do with the s. And then square root the things you can square root. So the square root of 36 is 6. The square root of this s squared is s. So I do those square roots, and what's left, things that I couldn't square root, are the 2 and the s. They're not perfect squares, so we just leave them under the radical. Okay, and then I can take the square root of the 4, and I get 2. But nothing else is a perfect square, so I just leave them under the radical. So I have 2 square roots of 2s. And then I have square root 2s on both the top and the bottom, and they cancel. 6s over 2 simplifies to 3s. Number 6, 8x minus 3 squared. That means 8x minus 3 times 8x minus 3, right? Exponent means repeated multiplication. So we write it out, and then we do FOIL, first, outer, inner, last. So the first terms, 8x times 8x is 64x squared. Outer terms, 8x times negative 3 is negative 24x. Inner terms, negative 3 times 8x is negative 24x. And then last, negative 3 times negative 3 is positive 9. And then we just combine like terms, so we have 64x squared minus 48x plus 9. Number 7, factor completely. I'm going to pull out the GCF first, the lowest power of x that appears in every term. So I'm going to pull out an x squared and think of this as reverse distributing. What has to go in the parentheses so that when you distribute an x squared to every term, you get this back. So I would need x squared plus x minus 6. And then what's in this parenthesis here is further factorable. I can factor that even more. It is x squared times x plus 3, x minus 2. Do a quick check on that. First, x squared. The outer is negative 2x and the inner is 3x, so those would combine to a positive x. And then 3 times negative 2 is negative 6. So just a quick reminder on how you get this. You're looking for numbers that multiply to negative 6, but add to positive 1. So 3 and negative 2, they multiply to negative 6, but they add to positive 1. Okay, number 8, the cube root of negative 125. Okay, so I need a number that when I multiply times itself 3 times, I get negative 125. So it's got to be a negative number, because a negative times a negative times a negative will give me a negative. Okay, so I'm looking for a negative number. And I'm thinking maybe 5, right? 5 times 5 times 5, negative 5 times negative 5 times negative 5. It's definitely going to be negative, and negative 5 times negative 5 is positive 25, and 25 times 5 is 125. So the cube root would be negative 5. And another factor completely, This is another difference of squares. X to the fourth is a perfect square because it's x squared squared. And 16 is a perfect square, it's 4 squared. So this is going to factor to x squared plus 4, x squared minus 4. And then x squared plus 4 is as far as we can go. It doesn't factor any further because there is no formula for the sum of two squares. But the difference of two squares, which I have right here, can be factored further. So this is going to be x squared plus 4. That's just being copied from the previous line. And then the x squared minus 4 factors to x plus 2, x minus 2. Number 10, we are dividing fractions. So multiplying or dividing fractions, first thing you should do is factor everything you can. So if it's factorable, factor it. So 6x squared over x squared minus 1 factors to x plus 1, x minus 1. And then we're dividing by 3x squared plus x. Well, I can factor out an x, and I'm left with 3x plus 1. And I have x minus 1 on the bottom. Can't be for any further factored. And then we remember that dividing fractions, dividing by a fraction, is the same thing as multiplying by its reciprocal. So I have 6x squared over x plus 1, x minus 1. And then I'm going to multiply by the reciprocal of the next fraction, x minus 1 over x times 3x plus 1. And then I'm going to cancel anything that is the same on both the top and the bottom. So I have an x minus 1 and an x minus 1. And then I have 6x squared, so one of those x's can cancel with the one on the bottom over here. So that x can cancel with one of those x's. And I'm left with, on the top, I just have a 6x. And on the bottom, I have x plus 1 times 3x plus 1. Okay, 11, I want to add two fractions, so I need a common denominator. So the common denominator is going to be the product of the two denominators. So I'm going to have x over x plus 3, and I'm going to multiply by the other denominator over itself. And then I'm going to do the same thing with 5 over x minus 3, multiply by the other denominator over itself. Okay, so I have, when you multiply fractions, multiply both the tops and the bottoms. So my numerator in the first term is going to be x squared minus 3x over my common denominator x plus 3, x minus 3. And then my second fraction, I'm going to distribute that 5 to the x plus 3, and I have 5x plus 15 over x plus 3, x minus 3. And now I have two fractions with the same denominator, so I can just add the numerators. So I combine like terms, and I'm going to have x squared plus 2x plus 15 over x plus 3, x minus 3. And I think that numerator does not factor. So 3 and 5 would multiply to 15, but 3 and 5 add to 2. Negative 3 and negative 5 would multiply to 15, but they would add to negative 8. They don't add up to the positive 2. Okay, so I think I am done. That's as far as I can go. Okay, number 12. Okay, 16 to the negative 5 halves, crying baby and a fractional exponent. So first, we take care of that crying baby. That's always first priority. So I'm going to move that, that whole factor, 16 to the negative 5 halves, put that down for a nap. Baby immediately stops crying, and the negative becomes a positive. What's left in the numerator is a 1. And then the fractional exponent, now we can deal with that. The 5 is a power, the 2 is a root. So this is 1 over the square root of 16 to the 5th. The square root of 16 is 4, so this is 4 to the 5th. And 4 to the 5th power, we might need to grab a calculator to do that. I think it's 1,024. Let me just double check. Yeah, 1,024. So this is 1 over 1,024. Number 13, we want to do 2x to the 5/4, all raised to the 4th power. So this is a product, which means I have to raise both factors to the 4th power. So this is 2 to the 4th times x to the 5/4 to the 4th. Okay, well, 2 to the 4th, that's just 2 times 2 times 2 times 2, which is 16. And then in this part of the problem, when you're raising a power to a power, you multiply the exponents. So 5 divided by 4 times 4, the divided by 4 and times 4 cancel, and you just get x to the 5th. In 14, first I'm going to, this is all multiplication, 5 times x to the 1/2 times 4x to the 3/4. So multiplication is commutative. You can do it in any order. So I'm going to rewrite this as 5 times 4 times x to the 1/2 times x to the 3/4. And then the 5 times 4, that's easy. You get 20. And then x to the 1/2 times x to the 3/4, we're multiplying like bases, so you should add the exponents. So adding fractions, you can either grab a scientific calculator and have them add it, or you can say, well, 1/2, that's the same as 2/4. 2/4 plus 3/4 would be 5/4. So this is 20x to the 5/4. Okay, 72x to the 6th over 9x squared. So 72 divided by 9, that is an integer. That comes out to 8. So I get 8. And then x to the 6th means x times x times x times x times x times x. And then I'm dividing by x squared, which is x times x. And then you can cancel things that they have in common. So there's 2 x's on both the top and the bottom. And I'm left with 4 x's on top being multiplied together, which is the same thing as x to the 4th. So I have 8x to the 4th. Okay, for 16, we're going to reduce 10 plus or minus 5√2 over 5. So you can break it into 2 fractions. So this is the same thing as 10 over 5 plus or minus 5√2 over 5. This is allowed because these 2 fractions that I just wrote have the same denominator. So if I wanted to add these 2 fractions back together, I would just add the numerators, and I would get 10 plus or minus 5√2 all over 5. I call this unadding fractions sometimes. If you take a fraction that has just a single term in the denominator, you can break it into 2 fractions. And then each of those can be reduced. 10 over 5, that's 2. And then here my 5's cancel, and I get plus or minus √2. For 17, we have 2/7 to the 0 power, which is 1. Anything to the 0 power is 1. So we have 1 minus 32 to the negative 2/5. We got a crying baby. We got to put it down for a nap. So I'm going to take that 32 to the negative 2/5 and move it to the denominator. So I have 1 minus, make a fraction, and that 32 to the negative 2/5, we put that down for a nap. And what's left in the numerator is just a 1. And then I can deal with the fractional exponent. So the 2/5 power, that means the 5th root and squared. So the number on the bottom of the fraction is the root. So I have 1 minus 1 over the 5th root of 32 and squared. So the 5th root of 32, a number times itself 5 times, that gives you 32. It's got to be 2. Check it. So 2 times 2 is 4. times 2 is 8, times 2 is 16, times 2 is 32. I was counting how many 2's I did on my fingers, and that was 5. Okay, so I have the fifth root of 32 is 2. So this is 1 minus 1 over 2 squared, which is 1 minus 1/4, which is 3/4. And last problem, I'm dividing two polynomials. So I am going to factor as much as I can. Maybe something will cancel. So x squared plus 3x minus 10. Let's see, this could factor to x and x. And then I need numbers that multiply to -10 but add to 3. So I'm thinking maybe plus 5 and minus 2. Those multiply to -10, but they add to 3. And then you do a quick check. You do firsts, x times x is x squared. Outers, and I get -2x, and my inners is plus 5x. So when I combine those, -2x plus 5x does give me positive 3x. And then 5 times -2 is the -10. And then I do the denominator. Again, I'm going to try to factor this. So I have an x and an x. And then for the numbers, I need numbers that multiply to -8 but add to positive 2. So I'm thinking plus 4 and minus 2. And I double check. X squared minus 2x plus 4x. That gives me the plus 2x, and then minus 8. Great. And then I'm going to cancel any factors that appear on both the top and the bottom, like the x minus 2's. And my final answer will be x plus 5 over x plus 4.